Good morning, ladies and gentlemen. I am very glad to be here. In the beginning, I will talk about structural anchors and their failures. My name is Lucie Malikova, and together with my colleague Miarka, we are employees of two institutions of the Institute of Physics of Materials, Czech Academy of Sciences, and also Institute of Structural Mechanics at the Faculty of Civil Engineering of Brno University of Technology. Both of the institutions are located very close to each other in Brno, which is the second largest city of the Czech Republic. And as you can see from the map, the journey to Rimini was quite long. It took about 12 hours by car because it's about 1,000 kilometers. Okay, so let's start with scientific program of my presentation. I would like to ask you for a little bit of indulgence because the presentation is actually part of our project that has just started. So it's the results are very pilot ones. So you will see what we have done. Okay, so structural anchors and the failure modes. I will show you some pictures how it works in these structures. I will tell you something about our motivation and our goals. I will present you the geometry we have investigated in our finite elements simulations. We want to actually compare the results of experiments with results of finite element simulations. We dealt with two different geometries. We had structure with bits accurate and without accurate. At the end, I will take some conclusions and, of course, someone acknowledge them. So, structural anchors are components that are often used to connect various elements of structure, mostly to concrete material, concrete substrate. Here you can see that there are many types and shapes of the anchors. So it is necessary to perform extensive research on effects of various parameters of these anchors. The anchors can be divided according to the way of their installation in the concrete. We can distinguish cast-in or post-installed anchors, and we also can distinguish the anchors according to the kind of their loading. We can load the anchors in tension or in shear. So here are some pictures as I promised. So at the right side you can see the kinds of shear loading and shear failures of the anchors. We can distinguish steel failure when the steel anchor is sheared. We can distinguish pre-out failure when a part of the concrete along the anchor fails, and then we have concrete edge failure when a part of the concrete at the edge fails. For me, are most or more interesting tensile failures. Again, we can have several ones. Steel failure when the steel anchor is torn, and float failure when the steel anchor is pulled out from the concrete, type phase blowout, then the part of concrete at the face of the anchor is or fails, then concrete splitting, when the concrete substrate fails or splits at the location of the anchors, and the more interesting kind of failure that we actually investigate in our research, in our project, is concrete cone failure, when the concrete cone around the anchor fails. So, as I said at the beginning, we try to find or explain why the crack propagates from the anchor under concrete direction, which was observed experimentally. We are in the literature. There is the angle of about 37.5 degrees, and we try to find explanations, some stress distribution or some fracture parameter that would explain or why the crack propagates in this direction. As you know, concrete is very non-homogeneous material, so the crack propagation in such materials is very complicated. So we had to make some simplifications in our pilot studies. Oops. Oh. Okay, so this is our geometry that we considered. We considered cylindrical geometry, so we could model in our finite element simulations only one slice of the specimen. So you can see two geometries with the crack and without the crack. Here is the anchor, which is embedded in the concrete substrate. Here is the symmetry axis of the symmetry, and the parameters, the values of the parameters are in this table, where you can see the radii of the individual parts of the specimen. You can see the specific lengths of the parts of the model, and we varied three parameters: the crack length, the initial crack angle, and the radius, where we investigated the stress distribution. Here is an example of our finite element models. We used ANSYS commercial software, and we created the model with plain 183 elements, because these elements enable better to model the crack singularity at the crack tip. And of course, we have to refine the mesh at the important places, such as the crack tip or at the corner of the anchor. Because the geometry of the specimen is quite big, and we had to apply this refinement. The element sizes varied between several hundreds of millimeters up to approximately 20 millimeters at the end of the specimen. Okay, here are again some more information about the finite element model. As I said, we use axial symmetry boundary conditions. At the beginning, we start with linear elastic material models for both materials. We used 210 gigapascals of Young's modulus and 0.3 Gaussian ratio for steel and 23.5 gigapascals Young's modulus and 0.2 Gaussian ratio for concrete. The anchor was loaded via tension, and we applied displacement of 0.05 millimeters on the upper surface of the anchor. As I said, we varied 3 parameters. We assumed 2 variables crack lengths, 1 at 5 millimeters, several crack inclination angles from 25 to 45 degrees, and we tried to investigate stress distribution at 5 radial distances from the anchor's corner from 1 to 5 millimeters. Okay, this is the configuration with a crack. For a crack, the most most important fracture parameters are stress intensity factors that describe the stress amplitude at the crack tip. And we calculated K1, K2 for loading for 1, loading 2, and then we used this formula for calculation the effect of both components. And we calculated the so-called K effective. This we have done for 2 crack lengths and several crack inclination angles. Here is only some note how we calculated the stress intensity factors. We use the command kcal implemented in ANSYS. This command uses the basic formula for displacements of nodes at the crack tip. So we have to define 5 exact nodes, which are parts of the first element at the crack tip. We define their polar coordinates, and together with their displacements, the ANSYS enables to calculate K1 and K2. Oh, sorry. Okay. That's all right. Here. Sorry. Here are our first results. These are dependencies of the K1, K2, and K effective. Blue is K1, orange is K2, and green one curve is for K effective. We compare the results for the crack of the length 1 and 5 millimeters. So be careful about the scale of the vertical axis. Of course, the values for large crack are higher, but the trends of the curves are same for both crack lengths. We can see that K1 decreases a little bit when the crack starts to be more vertical. On the other hand, the values of K2 starts to increase from the angle about 28 degrees. But the value of K effective, which should include the effect of both loading modes, stays more or less the same. So unfortunately, none of these curves explains why the graph should propagate under the angle 37.5 degrees, as was observed from experiments. Our results show that maybe the graph should have the same energy for propagation for every angles that we assumed. So we try to find another way how to explain this graph propagation. This is again what I have said. I think I've not forgotten anything. So let's go. So we start to find another parameter how to explain this graph propagation, and we created a finite element model without the graph. We investigated various stress components at the radius around the back corner, and we considered these radii between 1 and 5 millimeters. We investigated at the path for angles between minus 90 degrees, which is this edge corner, the edge part of the archer, to 180 degrees, which is this horizontal part of the archer. Wait, okay, it's I'm right. We use something like MTS criterion. Nevertheless, we have no break, but this is also stress concentrated. So we, when we had when we investigated several stress components, the only one that is close to the value of the 37 is this tangential stress. So when we did, or when we showed this dependence of the critical angle for maximum tangential stress on the critical distance, we can see that the angles are about 30 degrees, which is quite close to experimental results. Of course, we will do more complex analysis to obtain much better results. Sorry and thank you for your attention.